Hello everyone. Today we're going to be solving the 2020 AMC 12A problem 11. And after we solve this problem, I hope that we can generalize it and then learn about the total law of probability and then learn about some harmonic functions, discrete harmonic functions, and Dirichlet problems. Okay, a frog sitting at the point 1, 1, 2 begins a sequence of jumps where each jump is parallel to one of the coordinate axes and has length 1. And the direction of each jump, up, down, left, to right, is chosen independently at random. The sequence ends when the frog reaches a side of the square with vertices 0, 0, 0, 4, 4, 4, and 4, 0. What is the probability that the sequence of jumps ends on a vertical side of the square? Okay, I want you guys to try to solve this first before I solve it. You can pause the video if you want. I'm going to start solving. Okay, so I've drawn a little diagram right here. Here, let me just move it up so we can solve the problem. So this is the frog, and this is 0, 0, and this is 4, 4. So what I'm thinking is that this point looks really symmetrical. So if I start at this point, the probability of getting to either side. So wait, we want to end on the vertical side, right? Hold on. I'll mark the vertical sides first. So I'll mark this side, this horizontal side red, because we don't want to go there. And then I'll mark this side blue. Okay. And I'm just trying to see where it's most symmetrical. So over here, we have this line of symmetry. So the probability of getting to either one of these sides is just 1/2 because, symmetrical. So they're both equally likely. And same with this one, it has a line of the symmetricity here and here. Line of symmetry here and here, my bad. And this is symmetrical to this one. So these are the probability of getting to the blue side from these 3 points is 1/2. And then the probability of this side is obviously like once you already get here, you won, right? So what that means is what we can do, probability of getting to this point is 1/4, and then the probability of winning when we get there is just 1/2. So if we have pxy as our probability of winning from point, or I'll call it p1, 2 as our probability of winning from point 1, 2, it's going to be equal to the probability of getting to this point and winning plus the probability of getting to this point and winning plus the probability of getting to this point and winning and plus the probability of getting to this point because it's a guaranteed win. And this is just equal to 5 over 8. Let's see, 1 over 8, 1 over 8, 1 over 8, 2 over 8, 5 over 8, yes. So that means answer to this problem is B. Okay, how can we generalize this? Well, we can see from this question, we can just factor out 1/4 from the probability. So let's try doing that and see if it's revealing of anything. Sorry if my voice sounds kind of bad today. I don't know. I don't know what it is. Well, this is looking a lot like an average. It's looking like the average of the surrounding points. So maybe you just find the some of the probabilities of these points of winning from the points that are surrounding it, and then you divide it by the total number of points, which is basically just finding the averages of the probabilities of winning from these points. So we can write down the equation, probability of winning from a point xy, considering that p0, probability of winning from this, or from this row of points. So I'll just change it to probability of winning from, change it to probability of winning. Hold on, how do I even erase up this thing? Okay, you know what? There you go. So obviously the y-axis is always going to be 0. So this is going to be the probability of winning from points 0 to 4 is equal to 100%. And then the probability of, oh wait, and you know what, guys? I'm just not going to write these boundaries because they're kind of weird. But basically, we know that if we start on this point, we already won. And if we start on this point, we already lost. So we can just generalize it so that it's equal to the average. So the total number of points times the probability times the sum of the points, so sum of the surrounding points plus. So there's the probability of winning from the point above, and then below, and then to the right. So the right, and then to the, let's see, then to the left. Oops. So we also already know that the points, so you guys might be asking, okay, well, what if I start here or I'm out of the bounds? Well, we already have defined those points. I haven't written it down, but just pretend I defined it. Pretend I defined it, okay? Pretend I already defined those bounds. So this holds for any point, considering we have those boundaries. And this is literally this is basically just the total law of probability. It's basically the probability that you will get to one of the boundaries or get to your target boundary is equal to the average of the probabilities of getting to the boundary from the surrounding points. Um, hold on. Okay, so I won't give the proof for that. Okay, I'm not gonna give the proof for that. Actually, why not? Okay, wait, let me see. There's actually a really nice proof for it. Okay, so let's just say we have an event E, and for example, we'll call this event, we'll say that the event E is the probability of you passing a test. So we have students who studied and we have students who didn't study. So let's say probability of F, these are the students who studied, and this is their probability of passing. Studied and passing. Uh, Okay, whatever. Wait, never mind, never mind. This is the students who studied. So this is the probability that they studied, and then probability of G is they didn't study. So no study. I'm not sure right now. Okay. So basically what the total law of probability says is that it starts with this. The probability the the, the probability that the the portion of students who pass the test, so the percentage of students that pass the test is equal to the percentage of students who studied. This is an F, by the way. I hope that's clear. It's kind of not clear. Is equal to the probably is equal to the number of students who studied times the students who studied and passed plus the probability of or plus the probability of students who percentage of students who didn't study and passed, which is basically what this is saying. And then you can use this, and then you have the equation. Okay, you know what? That's whatever. Well, this is basically the total law of probability. Oh wait, no, no. This is basically the start to the total law of probability, and then this is literally just equal to this. But yeah, and then this total law of probability leads to harmonic functions, which are basically functions that are just the average of the 2 points that they're surrounded by. So you guys could probably guess that these functions are in the form. So if you have all right, here, I'll go over more of it. If you have a set of elements, let's call it S, and the elements are from 1, 2, 3 to N, and then you have a boundary set. Oh, oops. You have a boundary set that's equal to these boundaries because, like in our frog problem, our boundaries were the vertical and the horizontal walls. The boundaries of this are these are 0 and n. These are like the ending points. Like if you're on a line graph like this. And then our interior ones, I'm not gonna call it I, I'll call it L, I guess. And that looks kind of weird. Okay, I'll call it L. And these are gonna be our interior things. I'm just defining this so we can speak clear. Okay. So basically a harmonic function is one that is a set, it's in the set of, it traverses the set of S, or it's in the set of S, and it follows the property f of x is equal to f of x minus 1 plus f of x over plus 1. And the reason I set these boundaries is so that we can know, okay, well, when I'm here, I don't have a f of x plus 1, so we'll just know, okay, well, it's our boundary, so we're gonna have some set value. So this is basically a harmonic function. And in our frog problem, okay, harmonic. And our frog problem is actually a function. It's a harmonic function because it's the average of the points surrounding it. But this is a discrete one because it's bounded by it's bounded by the square, right? And the cool thing about these harmonic functions is basically what I was trying to get at with the harmonic functions is that these harmonic functions are what we need to are basically bring the question of what the Dirichlet problems are. Dirichlet problems are. Hold on. Dude, this guy's name is so hard to spell. Dirichlet problems are. Because these Dirichlet problems ask, okay, well if I have some question that if I have some set like this, or if I have a question that's asking me like what is the probability of getting over here of what is the problem of getting to one of these boundaries um inside of this set starting from some point x, it basically asks what harmonic function what's the harmonic function for one of these sets. That's basically what the Dirichlet problem is asking. And that's really all I wanted to go over in this video. I'm sorry if the explanation is kind of bad, but I hope you guys learned something. Yeah, thank you for watching.